All right, welcome to topic number 5 in Unit 3, which is rates of radioactive decay, rates of decay. We've already done the actual types of decay in topic 4. So we're going to do the rates and half-life calculations in this topic. Now some of you are going to be quite familiar with this because you have done it in math class, but just in case, we'll run through the procedure. Now, what we mean by a half-life is the time it takes for 1/2 of the nuclei in a sample to decay by spontaneous emission. Now what we mean by spontaneous emission is they spontaneously undergo one of those types of radioactive decay that we talked about in topic 4, alpha, beta, or gamma. Okay, so that's the half-life. Now for carbon-14, for example, which is the thing that's used in carbon dating you may have heard of, 1/2 of all the nuclei will decay in 5,730 A, which means annum, or years. So it takes 5,730 years for half of the carbon-14 nuclei to break down. So at the end of 2 half-lives, or in other words 11,460 years, 1/2 of the remaining nuclei will decay. Now carbon is very useful for carbon dating, for dating things, because carbon is a very, very common element. It's found in most living things. So if you want to date something like a fossil, or you want to date like an old plant matter that you found, you can use carbon dating. Anyway, after 3 half-lives, there's a half times a half times a half, or 1/8 of the originals left, and so on and so on. So mathematically, we can calculate that using this formula. This is the half-life formula. That's on your formula sheet. Now the one you've used in math may be slightly different, but it should give you the same answer. So if you'd rather use the math one, you can go ahead. But this one is designed to be able to do the calculations that we're going to do. So A is the amount remaining. A0 is the original amount. Then the half is always there. And T is the time. T subscript 1/2, that's the half-life. These amounts, by the way, can be a bunch of different units. They can be masses, they can be a number of nuclei, they can be a radioactivity, a measure of radioactivity, which we're going to look at now in a second too. But it doesn't matter what they are. It can be a percentage. Okay? Whatever they are, you can fill them into that equation. Here's what it looks like on a graph. What you end up with is an exponential decay curve. Starts high, and it gradually starts to level out. That's an exponential decay, and that is what half-life looks like. Starts out with this. At the first half-life, we're down to a half remaining. By the time we get to the second half-life, we got 1/4 of the original remaining. The third half-life, we've got 1/8 of the original remaining, etc., etc., etc. That's an exponential decay graph. Here's an example for a particular element, radium, which has a half-life of approximately 1,600 years. So we start with 100%, we get down to 50% after 1 half-life, which is roughly 1,600 years. Then after 3,200 years, we're down to about 25% left. After 4 half-life, or third half-life, okay, after another 1,600 years, now we're down to half of that again. So half first. First half-life was 50%. The second half-life was 25%. The third half-life we're down to 12.5%, etc., etc. It keeps getting lower every single time. All right, how do we apply that to radioactivity? Well, like I said, you can have a mass, you can have a number of nuclei, you can have a percentage, or you can have sometimes the rate of decay is usually given in becquerels, or BQ for short. It can also be kilobecquerels, megabecquerels, but a becquerel means 1 count per second. So for example, if you have a count of 1.5 kilobecquerel, that means that some recording device has detected 1,500 atoms, or nuclei, decaying every second. And one device that can measure that is something called a Geiger counter, that you've probably heard of before. And that was invented by a German by the name of Hans Geiger. Anyway, again, there's the formula. Very simple formula to use. However, if you've never used it before, it does involve the use of logs to solve, as you'll see now as we go through some of these examples. So let's take a look at some examples that have been found on old public exams. So the first one. Now this one's a fairly complex one for a multiple choice question. This is normally a 2 or 3 mark question on part 2. But occasionally they do show up in the multiple choice, so it's important to know how to do them and how to do them quickly. So remember the formula. A equals A0 times a half to the power of t divided by t1/2. So let's work it out. The amount remaining has to be 2.5%. The original amount then must have been 100%. And I got a half to the power of, the half-life is 14.7. T I don't know. So I do that first. Then I divide by 100. Hundreds cancel. And you got 0.025 is equal to, I'm going to make the half a 0.5, to the power of t over 14.7. Now, when you've got variables in the exponent like that, that makes it a little difficult to solve unless we use logs. So here's what I'm going to do. I'm going to take the log of both sides, 0.025. And when you take the log, you can do this. This is why we use logs in the first place. We can take the exponent and put it in front of the log. That's what makes logs so useful when we're solving this type of problem. That property, that particular property is the important one. Now all I have to do is divide both sides by the log of 0.5, like this. That cancels. And that leaves me with t over 14.7 is equal to the log of 0.025 divided by the log of 0.5 happens to be 5.32. Then all you got to do is cross multiply. So t equals 14.7 times 5.32, which means t equals 78.2, which is choice C. That's how you use logs to solve these exponential decay problems. And like I said, you've done that in math, or at least most of you have, so that should be a really quick review for you. Let's take a look at the second one. You don't need logs to solve this one. How much of a 60-gram radioactive isotope remains after 4 half-lives? Easiest way to do that is to say 60.0 times a half to the power of 4. That's 4 half-lives. Half to the power of 4, which is the same thing as 60.0 times 1 over 16, or 60 divided by 16, which is 3.75. So the answer is A. Now another way to do that, after 4 half-lives, just divide by 2 4 times. So 60 divided by 2 is 30, 30 divided by 2 is 15, 15 divided by 2 is 7.5, and then finally 7.5 divided by 2 for the 4th time is 3.75. That's another way to do it. That's pretty simple too. Then the next one, how many days will it take for this sample to decay to this? So in other words, we start with 100 and we get down to 12.5. That's actually 3 half-lives exactly. That works out to be exactly 3 half-lives. Now you can work it out using logs if you want, but if you take 100 and divide it by 2, keep dividing by 2 and see if you get to 12.5. 100 divided by 2 is 50. That's 1 half-life. Divide by 2 again is 25. That's 2 half-lives. Divide by 2 again is 12.5, which is what we're looking for. That's 3 half-lives exactly. So 3 half-lives, if the half-life is 5 days, would give you 15 days. 5 times 3. That's the simple way to do that one. Now you could set it up and use logs as well. That would work as well. But that's the simpler way to do it. That is the simpler way. Let's take a look at this one. We've got a radioactive material with this initial activity, and BQ stands for becquerels, remember, which means the number of decays per second. What is its activity after 9 hours if its half-life is 3.2? So how many half-lives are there? Well, 9.0 over 3.2. And 9.0 divided by 3.2 happens to be 2.8125. 2.8125. So the amount remaining is going to be 1,320 times a half to the power of the number of half-lives, which is that number. Now you need to know how to do that on your calculator. On some of your calculators, the button will look like this, if you've got a graphing calculator. Or it might look like this, y to the power of x, or it might be x to the power of y, but those are the buttons you have to look for. So if you're not sure how to do that, ask someone in your school, ask your math teacher or your science teacher how to do that calculation on your calculator, because that's a fairly easy one to do if you know how to use your calculator properly. Anyway, in this case, that happens to equal 188 approximately, which rounds off to 190, or A. Okay, the next one asks you to find a half-life again, but this time it asks you to find it from a graph. Well, all you got to do, look at the starting point. There were 16 grams initially. So half of that would be 8 grams, which is this point on the graph. That's 3 hours. There's a half-life. That's a half-life, straight off the graph. Simple. No calculation necessary. You should be able to do that very, very quickly. Take it right off the graph. Half the mass remains after a time of 3 hours. Next one. We got an initial activity of 1.50 times 10 to the 6. After how many half-lives will the activity decrease to that? Well, let's do the division again. Okay, I got 1.50 times 10 to the power of 6. Divide by 2. That's 750,000. Divide by 2 again, and I get 3.75 times 10 to the 5. That would be 2 half-lives. In other words, it's been cut in half twice. So the answer is C. Now you could do that using your logs, again, using your half-life formula, but it's a lot easier to do it just by simple division because it's a nice whole number. And often in the multiple choice, that's the way they do work out. That is the way they do work out. Okay, they try to keep them relatively simple. Okay, this last one here in the multiple choice would be, it decays to 65% of its original. Now, because it's 65%, that's not a full half-life yet, is it? That's not a full half-life. So in other words, the half-life is going to have to be less than 15 days. Or sorry, greater than 15 days, I should say. Because after 15 days, it's still not down to half. So the half-life has to be greater than 15. So it can't be this and it can't be this. So if you weren't sure how to do the calculation, at least now you've got a 50-50 chance of guessing it correctly. But if you want to be sure, use the equation. And the half-life formula, like I told you, is on your formula sheet. Okay, you don't have to memorize it. It's there. So the amount remaining is 65%, which means the original amount was 100%. So we can just do it like that. Times a half to the power of. T, we know it's 15 days. T 1/2, we don't know. So I divide by 100 on each side. And that gives me 0.65 is equal to a half to the power of 15 over T 1/2. Okay, so you solve that the usual way using log. So you'll get the log of 0.65 divided by the log of 0.5, and that's going to equal 15 over the half-life. And when you solve that, you get a half-life of, let me see, let's work this out. I thought I had it worked out, but the answer I got doesn't make sense, so I must have done it wrong. The log of 0.65 divided by the log of 0.5 is equal to 0.621. And that equals 15 over T1 half. So that means that the T1 half, your half-life, is 15 divided by 0.621. And 15 divided by 0.621, 15 divided by 0.621 is actually 24 days. And the answer then is D. The answer is D. Now, if you multiplied 15 by 0.621, you'd actually get 9.3, but that would be the wrong answer. Okay, that would be if you use 15 as the half-life instead of as the time. Okay, so that's it for the multiple choice. Those are the types of the multiple choice usually don't require a big calculation like that. They usually save that for the second part. Usually, like it's a whole number of half-lives, like it was in that one. That's the usual thing. Now, like I said, every now and then one does slip in that has a little bit more work. So do be prepared for it. But usually that type of one is on the second part. Iodine 131 has a half-life of 8.04 days. That's the T1 half. The sample originally had an activity of 2.0 times 10 to the 6. We want to know how long will it take to have an activity of 1.85 times 10 to the 6. Now that's obviously not a full half-life. So here's the way you do it. Here's the answer. You start out with the half-life formula, given. Then you plug your numbers in. Now you don't have to put the units in if you don't want to, but you can if you like. It's up to you. So there it is. The original amount was 2.0 times 10 to the 6. The amount remaining is this. Time we don't know, but the half-life is 8.04. We do know that. So you divide both sides, first of all, by 2.0 times 10 to the 6 to get that. Okay, that's going to equal 0.925 is equal to a half to the power of t over 8.04. Now you use logs. And when you use logs, you can take that exponent down in front of the log. That's the whole point of using the logs in the first place. Then you divide both sides by the log of 0.5 to get that, 0.1125. And the answer then, when you cross multiply, would be 0.904 days. Now, as I mentioned earlier in one of my topics, when it comes to Unit 3, most of the time, if there's a half-life calculation, that's the one that's designated for science and communication skills. In other words, the right number of significant digits is important, and the right units will be important. So the time in this one was measured in days, so we need days as our units, and we need 3 sig figs because all of our numbers there had 3 sig figs. Okay, so that would have been important in this question more than likely. Let's try another one. Same type of thing, only this time instead of being given a activity, we're given a percentage. But you do it exactly the same way. It's done exactly the same way. You start with the units. Or you start with the formula, sorry. And look, they actually gave a half mark on this exam for actually coming up with the formula that was given anyway. Then you plug in your numbers. Instead of saying 18 and 100, they said decimal 18 and 1. Same thing. The calculation is already done, right? You've already divided by 100, in other words. You've already changed the percent into a decimal. Okay? Now, you know the half-life, though, is 30 decimal 2. So we could actually put 30 decimal 2 right there. You can plug that right in there right away. So there's what you get. You do your logs. You divide. And this one, they did the logs first and then divided. But anyway, the answer is 74 years. Okay, 74. And only 2 sig figs this time because it was 18%. That's only 2 sig figs. Let's try another one. This time, instead of being asked to find the time, we're being asked to find the half-life. But it's exactly the same type of calculation. half-life formula. Only they used N instead of A. I'm not sure why. A is what's on the formula sheet. Okay, so you divide by N0, then they plug the numbers in. There they are. That's the numbers you were given, 1.35 and 2.00 times 10 to the negative 3, 10 to the negative 4. Divide those, and you get that. Okay, and the half, whoops, what happened? There we go. The half, doesn't want to delete for me, there we go. The half becomes 0.5. Now you take the logs of each side. So you take the log of the left and the log of the right. That brings the exponent down in front of the log, like that. Then you divide to get that. Okay, now again, they did the logs first and divided after. But you get this for the half-life. Okay, 0.77 hours. And again, on this particular test, that was a question that was graded for science and communication skills. So if you look at your units, it had to be hours for time, and a half-life is a time. And on top of that, we had 3 sig figs here, 3 here, but only 2 here. So your answer is only allowed to have 2 significant digits. So it had to be 0.77 and not 3 significant digits. That wouldn't have given you full marks. Okay? Last question. This one's a little different. This one you were asked to sketch a graph. Activity versus time. So it started at 100, it says. So let's plot some points. First point is 100. Then it says it's a half-life of 2.5 minutes. So that means after 2.5 minutes, we're going to be down to 50%. In other words, we're going to be there. After 2.5 minutes, 50%. And then after another 2.5 minutes, which would be 5 minutes, we'd be down to 25%, which would be roughly right there. Then after another 2.5 minutes, which would be 75 or 7.5, we'd be down to about 12.5, which would be roughly right there. Okay, what you need to do then is try to draw a nice smooth curve. Now, not easy to do on a tablet, but there you have it. Close enough. That's what it looks like. It's an exponential decay graph. Then it says, using that graph, determine the activity of the sample at 6 minutes. Well, here's 6 minutes right here, so there's your point. And the way my graph is drawn, that would be roughly 15 becquerel. Straight from the graph. I'm not asked to do a calculation. I'm just asked using the graph. That's it. I can take it straight off the graph. Now, if you wanted to do the calculation just to check it, wouldn't be a bad idea, because that's going to be off a little bit. That's only an estimate. But it's close enough for this. Okay? So that's a slightly different question, using a graph. And this is just an exponential decay. You plot your points, draw your curve, you got your graph. That concludes rates of decay and half-life. So that's topic 5. Now there's only one topic left. Topic 6 is all about the last part of the course, which is all about fission, fusion, and nuclear power. Specifically, the Canadian nuclear reactor, which is called the CANDU reactor. So we'll deal with all that in our next topic. So again, good luck, study hard, and if there's anything else that you're not sure of, you need some help with, come back and view those topics.